All right, the other thing is attendance. Today's the 27th. Wow. Where's this month gone? Shear. Okay, cool. All right, so let's go have some fun. I gotta get rid of these safety glasses before I strangle myself. All right, so let's go back here again, just to review. You guys can't see anything. That would be useful. How long would you let me talk before I looked over there and actually see the screen was on?
I would stop just bringing something pretty important.
Thanks, Frank. All right, so it's the uniformly distributed load on top of a uniformly distributed load. Break your point loads out in your free body diagram so you can figure out what the reactions are. And then we go back and do the shear diagrams, but you go back to the points where the uniformly distributed loads start interacting, okay? So it's not like I'm drawing lines down from my free body diagram directly. Make sense? So if I did this right, I gave you the C, the D, but I also labeled E, and I think we put an F out here, didn't we? Yeah, we put an F out here, okay? So knowing where all those points are is where you're going to put your line. So if you haphazardly draw a line at C down on the shear diagram, it will look okay, but the numbers aren't going to work right because your distances are going to be too far off. All right, so let's see how much fun we can have with the moment diagrams. Hey Frank, do me a favor, look in the book. Does he explain the moment diagram curves of the uniformly distributed loads, or does he not do that? We're going to need to talk about that otherwise. Okay, so bending moments. All right, go away. So at A, E, B, and F, okay? And this is our moment, and this is pounds, feet. We doing pounds, feet, okay? All right, so the very first bending moment is going to be what? Moment at A. It can't equal 0. It's going to. What's the first moment at A? It'll be 0, right? Because there's no distance. Okay. I even wrote it up there, and it's like, oh no. Okay. Now, how about the moment at E? But here's the interesting thing. So you remember this little gizmo here that did this bit? Yeah? Remember when that crisscrossed the line at 0 in the shear diagram? What did I tell you about things that cross the 0 axis in the shear diagram? Where the maximum moment is going to be. Or a moment. A max moment could be. You can have multiples. But, so, I hate to tell you this, but we kind of need a little line there too. Okay? So, now the interesting thing is we know, I think I'll move some numbers down here. We know that this is 7 feet, this was 6 feet, and that was 5 feet. Okay? What is this distance right there? Anybody know a way to figure it out?
We do it where we go by each, and then we'll split up to 0.
We could, yeah. Is that the easiest way?
Probably.
We know the shear is 0 at that point, yes. What's that? We're looking for the distance, yeah. Yep. We could. Do you know the angle? Sure, but you still don't know what the hypotenuse is. Good to think that way. Did he explain any of that stuff about these crazy curves?
A little bit, I think crazy.
Okay. Cool. So I want you guys to really go back and look at page 284 through 286 and read those so you understand the uniformly distributed curves and stuff that go with these guys. Thanks, Frank.
Yep.
So, what do we know mathematically about these problems? Nate, what can you think of that we could possibly have there that's going to make this easier? He fails. Somebody said, I think it was Carter, said we know where the 0 shear is. Right? And we just work some numbers out so we get the zero shear. Right? But what else can we figure out? We know at A it's 17.25 pounds. Go ahead. Okay.
We just do 17.25 minus 3 times the distance.
I know what I think you did. No. Yes. Right. Like let yourself, actually you can just write it right underneath there in the shear diagram. So the other thing I can think of making your life easier, if you knew what the slope of that line was, if you saw the mathematical equation that went with it. I see some heads kind of nodding, but they're bobbing like they're bobblehead dolls in the back of a car. Maybe. Couldn't you? It's kind of what Montana's writing down here. But if you yes.
Where's the three? That is the. Yeah.
Yeah, so 3 pounds per foot. Okay. Does that, by any chance, I hate to tell you this, does that look at all like y is equal to mx plus b?
Sadly,
Is that?
sadly, yeah.
Sadly, very much so, isn't it? Okay. Okay, you did it. I don't even know if you thought about y is equal to mx plus b, but that's what you wrote. Okay? I hate to tell you, the math world does come over here and hang out once in a while. Math chair usually in my office. But the little bit of this is 17.25 is the y-intercept, right? Or the, yeah, y-intercept. 3 is our moment, right? So for every number, or 17.5 is the b. Thank you. Good enough. But for every foot across, we're going to go over 3, or down 3 for every foot we move to the right. Yes? Let me draw it, just make sure you see it. Let's do it over here and we'll get it big enough so you can actually see it. So we're 17.25. That's y. And that's our x. Okay. And we're going down to here. So for every foot we go over, we are literally dropping 3 pounds per foot. Okay. So literally, that is gonna love this. Civils, don't get too excited here. Is that right? Now, does that even look more familiar to the math world? So what's the y parentheses 0? Find y with of a point 0, right? So basically, we can just solve for the whole thing is what Montana did. Yeah? Good? Okay. All right. So, what did you say it was? 5.75? Okay. So now that we know this is 5.75 feet, we are going to need the other rest of that for over here, but we can deal with that one in a minute. So we need to come up with a new point right here. So let's call it A, B, C, D, E, F, G, right? So that's our G. All right, the moment about G is MA plus our area of that triangle, right? One half 5.75 feet times 17.25 pounds. Is that really pounds or was that kips? Oh, it's kips. We've lost the kips in here someplace. Okay? Everybody good so far? But without that little intermediate step in there, you're SOL looking for something. Well, maybe not SOL, but you're going to paddle around the lake a lot before you actually get in a straight line. Okay. All right, so what do we got? By the way, so that's positive. This is, yeah, ½ inch. What do we got for a number? You guys are going to have to come up with the numbers because I haven't done this problem out yet. So as we do this, this is all on you guys. Right, Emma? Henry, you got a number? 49.59. Kip feet, right? Okay, so we need to pick a scale here somehow. So 49, so let's do 10, 15, 20, 25, 30, no, 10, 20, 30, 40, 50. So we're going to go just a little shy of there. All right, now, Frank. What did our friend Mr. Limbrunner tell us that the curve's going to be? Which way did it go, I guess? You're going to curve up this way, or is it going like this? Okay. So what I'm asking here, folks, is does the curve start here and go like this up? Or does the curve start here and go like that up? This one, okay? So it's going to do this. And if you wanted to, you could do the mathematical calculations for it, but it's more or less knowing it's going to get there. Why is that? Absolutely. What great problem in math do you see that in? I'm going to bring up something that's going to tie in the math a little bit, all this together. So remember I said when the line crosses the zero axis on shear, I am probably going to have a maximum moment. Okay? Why does the curve start tapering off slowly to 0 at the point G there? So, if you're ever looking for a maximum point of anything, maximum moment, maximum deflection, if you go back to calculus, we've had you calculate inflection points in curves, okay? And where's the inflection happen at? At a 0 slope, okay? Yes? Now, what about that shear diagram? When I told you that most maximum moments, or most moments that are going to be likely to be the max, occur at a shear of 0. shear and the slope are the same thing. Okay? Just to show that there is some relevance to stuff you learn over the math department. Okay? But either way, so we're good there. All right. Now we need the moment at E, and that's going to be mg minus rme, but that's going to be 49.59 minus, sorry, that's not me, that's our v at E times some distance. Okay, but we are a triangle there, right? And that triangle was, I don't know why I didn't write it in there, negative 3.75 kips. Okay, and we just figured out that this distance here was going to be 7 minus 1.2, or 7 minus 5.75. It'll be 1 point, what? Or actually, what's the distance? Just put it out there. No, that's not right. What's our number? What is it? 1.25, yeah. Okay, so we are back to 1/2 times the negative, what did I say it was? 3.75. That's a plus. And we know it's 1.25 feet. So 49.59 kip feet minus, what's the rest of this? 3.75 times 1.25 is what? Divided by 2? 2.34 kips feet. It's a negative, so really we're going to drop off what, 40, what's the final number?
47.25.
Thank you. 47.25. So we're coming down to here, and that's 47.25 kips feet. And curves like so. Okay? Everybody hanging in there? All right, that leaves us the next complicated one because we got the load, uniformly distributed load starting to pop over on top of each other. But the cool part is we got no more zero axis until we get to B. All right, so let's do this. I'm going to leave this just like that. You guys, all of you, work out what the moment is for B. B minus, actually, because that's a little bit just before. See that okay, Lois, or? I'll put it there for you for a second or two, and I'm gonna zoom back out so we can see the triangle. Now, we've done a problem like this already with that extra weight. If you go back and take a look. And I'm doing this on purpose because I want you to struggle here, so if I know you understand it, instead of me just telling you what it is. How's Fidel doing? Justin. How's Fidel doing?
He went to the hospital yesterday, but they ain't talking to me. They took x-rays, but they didn't see anything.
Got it, I should go off the board, put it up on the screen. It's okay. It's the first time someone makes a mistake. Oops. Everybody be nice, because you could have been the person chosen. Okay, what's everybody think? You got it. What you got? Cool. Two people agree. Carter?
That's what I got.
Montana? No?
I don't feel comfortable.
All right, before you got down, just walk everybody through and explain what you did, why you did it.
So on Shear,
You can zoom in on the screen. And if you flip the pen over, the top's in over.
So on the shear, you got this triangle and this square that you got to solve for the area. So then you subtract the 3.75 from the think it's 30.75 to get 27, which is this height here. And then this is 6 feet, and that's 3.75. So that's how I figured that out, I guess. I don't know.
That makes sense?
I use the link for BB and not BB.
Okay. Everybody else get it? Patrick?
I have it wrong, so.
Well, I know you had it wrong, but you see how he did this, and it makes sense.
Yeah, I see what you did.
It's okay to make mistakes, so I don't really, yeah, on a test, I'll grade you for mistakes. Homework, I'm gonna let you know you got a mistake, but it's only because you need to know where your mistakes are. In here, mistakes are freebies. Okay. Good, thank you. So other than, you need to draw a diagram now. I just thought of that, he came back down here. All right, so we're going to take negative 56.25 and put it on our diagram. So 10, 20, 30, 40, 50, 60. There's some place right about there. All right, now here's the interesting thing. Where is the curve going to go? It's going to go down. Is it still curved like this? Or should it start curving like that? So I could do one like this, or I could do one like that.
Second one?
Well, the answer really comes out of the shape of the triangle, folks. Okay? So when we actually get to here, we are looking more for this top one to be the curve, but it's going to wind up at a point. Okay? Did I do that right, Frank? Did you say anything in the book about that one?
I don't see it, but maybe. I don't think it will.
Part of me wants to be, let's do this. It's either the purple or it's the blue.
So why wouldn't it be the purple if you're going up again?
Well, that's kind of where I'm thinking it's purple. I want to check it, but it's, and the other reason I got something else in mind here too that goes with this. What it matters is this, folks. Okay. So little insight into the future. It's always good. So at this point right here, where I cross the 0 moment axis, okay, it's another maximum or midpoint. If we get some calculus here. But the one thing we haven't done yet, we won't do towards the end of the semester, is deflections. Okay? How much is this beam actually moving from center, up or down? Okay? And where the maximum moment occurs, not the maximum, where the 0 moment line crosses that 0 moment axis, the moment line crosses the 0 moment axis, here we go. That's the max deflection. So that's how much something's gonna fall out of its orientation. Okay? Mechanicals, that's very important because we're always worried about shafts and alignment between gears or bearings and all that other sort of stuff. And it'd be really funny to make something that does this all the time and have a problem. Civils, you folks are worried because wherever that's gonna be, we don't want our concrete breaking on a floor on a beam. Okay? And how far can you let that sag out of through center? You don't wind up having something flat. Okay? I'm gonna go with the purple right now, and I'm gonna go back and check the logic behind that. I'll let you know. But anyways, so purple down to here. Now, what's the next one gonna be mathematically? Anybody? Well, not anybody. Who's my next pigeon? It's literally just this triangle here, right? And if all things go well here, what happens? We go back to 0. So you guys calculate that, and there will be somebody coming up, put it on board. Pull that back down. Got it, Eric? Cool. I'm gonna get that Shear diagram out. And you're up. Go to the board. Go to the tablet. Two fingers, you can zoom in on it, you can zoom out.
Oh God.
The top of it's theoretic.
Yeah. Don't mind the handwriting.
Yes, maybe? Okay, so it looks like that. All right, so let me zoom out here for a minute. Everybody get the equation? I'll do that. Everybody get the equation you need? Okay. All right, let's go here for a minute and talk about some stuff. All right, so proof in the pudding, as they would say. So at G, we had a deflection in the moment, right? So we went to 0, or we went to the slope of 0. Okay? And that was where the shear crossed the 0 axis line, correct? Did the one at B conform to the same rule? Yes. Okay? So literally we have two moments that we're really interested in, but only one of them is going to be our maximum moment, correct? Now, when we're looking for the stress, so we go sigma is equal to MC over I, we haven't done yet because it's roll another day or so down the road here. We're going to take the maximum of those two, whichever is the big or small. Okay. Cool? Okay. Now, I'm going to take you back about, seems like a month ago, but I think it was only a week and a half ago. Remember when I said beams, if they smile, it's a positive bending moment. If they're negative, it's a negative bending moment. Okay. So if we take a negative 56.25 and we take a look at the stress that goes with that one, you're going to carry that negative with it, times the C, so the centroid of the part, okay, the shape, divided by its I value, correct? Which way is that going to go? Smile up or from? Beam's going to have a positive or negative curve to it. Smile was the positive.
You said you carry the negative sign with it,
Oh yeah.
so wouldn't it have to do that?
Yeah, so remember, this positive, that negative, okay? And the stress is positive and the stress here is negative, okay? So really, that goes back to the whole thing, and as long as we're having some fun here, there is another curve that we do that is deflection. So literally, this beam here is going to deflect this way until that point, and then we're going to deflect that way to that point, okay? And what we're really interested is how much distance, y-wise, did this thing deviate from its true center, okay?
So is that like basically kind of like the shape that it's supposed to?
It is the shape the beam will take, okay? So, a little sidetrack here for a minute. I just found the metal ruler blowing down the HVAC line, but remember I talked about tractor trailers, okay? Flatbed tractor trailers. The old heavy steel ones were always just done like this. And you loaded weight in the middle and they deflected like so, okay? Almost to the point that the front set of wheels in the back got all the weight and the back set got less weight. And if the tire was going to blow, it always blew on the front set. Very rarely just blow on the back set. Okay? Then they went to light aluminum frames, and they did this pre-tension stuff where they actually made it go this way. Okay. Now, when that gets loaded, it straightens itself out. So now everything sits where it's supposed to, and everything wears evenly. Tires don't blow on the highways as much as they used to when I was a kid. Okay? Tires still go, but we really get this. Can I borrow you from that? Just read that so everybody can see it. All right. So as we bend this top side is in tension. Okay? This bottom side is in compression. We're squeezing the metal fibers back together in the bottom while we're stretching them out the top. Okay? But the neutral axis bit that I talked about is got no stress on it. Okay? So the bigger the beam, The more tension there is on top, and the less here. So what shape of stress is on this beam? Negative. Oh. Now what do we do this? Which side's in tension, which side's in compression?
Top.
Top's in compression, the bottom's in tension, okay? And that's gonna be important to you somewhere down the road in the future, okay? Not so much here in strength, but when you get to the design course, knowing whether your beam is like this or like this, okay, will play havoc with the rest of your design. Okay? Keep that in mind. All right. Everybody good? Everybody kind of getting the gist of this? Okay. Now, let's pick, we're not doing another one today, but now we get that. What's that?
So now we got time.
Oh, yeah, we rushed through it in the lightning speed. I would say this for sure, okay? You should be able to do 13.1B. Let's do 13.3B. All right, I'll give you a choice. Who did I pick on today? Justin. You got yours with you? Okay. Of these two here, choose one. Okay. 13.12A. Ooh. Okay. And I'm going to choose one of the 13 ones. 13.13. A. You don't want to do B? Why not? All right. And 13.13A. All right. Then choose the next one on 15. A. Okay. And I'll put those up so you know that that's the homework. Now, so we'll do a couple more of these on Friday. The other thing is I'd like to do this Friday. I'd like to give you a little quiz on one of these. Not one of these, but a simple one. So first thing Friday morning, we're going to do a quiz, and then we're going to go crank out some more of these. So, practice, Carter, okay? All right, folks. Other than that, have a good day. And how often do you get a quiz told you ahead of time?
I don't know